the traction vector Ti. In some books, this is also called as the stress vector. And what we have is this Ti. So, if there is a point P on the surface, surrounded by an infinitesimal area dA, then the surface force on the area dA per unit area is called the traction force. So, the surface force per unit area is traction force. Now, which quantity do we know is any force per unit area? Pressure. So, it will turn out that pressure is one of the one special type of a traction force. So, what exactly does traction give to you? It gives you the intensity of the force. And you know that's important. For example, if you step on a stone, you are putting some force, or if you step on a pin, which hurts you more? When you step on a pin. Why? Because the force per unit area is much higher when the area is that of a pin compared to that of a flat stone or a flat surface. So, therefore, traction, when we talk of, it gives us an idea of the intensity of the force. So, traction is basically related to okay. Now, why does it become important in mechanics, particularly in solid mechanics? Because this intensity of force is related to the failure of a material, which the example which I showed, which I just discussed, our skin is there, it is intact if there is a lower intensity of force. But if on the skin we apply a very high intensity of force or a high traction, then the skin fails. It breaks, we have bleeding, it hurts because the nerves get affected. So, this intensity of force is therefore very important as far as when we talk about solid mechanics. Because this is what will tell us when a material fails or when it does not fail. And so, its importance is fairly obvious. Now, let us look at this, that this is the area dA, and area dA, its direction is given by the outward normal n to the area. At that area A, we look at the direction perpendicular to the area. In the limit that this area is very small, it is planar. So, perpendicular to it, we will have a direction. That is what we call as the normal. Now, why do we use the term outward? Outward means that this area is covering a volume. So it is outward to the volume. That is the meaning of outward. So now, if we have a surface force acting and we have this outward normal n, the traction force, if we call it as, or traction if we call it as Ti, then Ti multiplied by dA, what will that give us? That will give us the surface force on this area. Okay? Now, this, what we can see is this. So now, the direction of Ti need not be along n. It can be in any general direction. Okay? So now here you see physically what we have are two vectors. Which are the two vectors? N and Ti. Okay? Now, the component of Ti along n, what is that? It is basically force per unit area. In general, force per unit area we call as stress. Okay? So, the component of Ti along n is a force. What will it tend to do to the area? It will either pull it or push it if it is negative. So we call that as the normal component of Ti. Okay? So now we have on area dA, n is the outward normal, and let perpendicular to n so one direction is n, and in the plane of dA we can find two perpendicular lines which are at 90 degrees to n. Let me call them as S1 and S2. So now what we know is, in general, T will have three components. A component of T along n, component of T along S1, and component of T along S2. Okay? Is that clear? And what will be the force? Force will be T multiplied by dA. Whatever is that component, we multiplied by dA will give us the force in that direction. Okay? So now the component along n is what we will call as the normal stress. And what are these two components called? They are called the shear stresses. They are component of the traction force in the plane of the area dA. So these two components collectively, they are called shear stress. Okay? So this is a physical interpretation which I am going, and now very soon I am going to define and get to a mathematical definition of stress. But what we realize is that at the point P, depending on the orientation of n, T can have or T is still the same, the no, this is not correct. Let me be a bit more. I'll just. At the point P, I choose the area dA, but then I can have different orientations of the area dA. So therefore, what I have, you realize, is this: I have a traction vector, I have an area vector dA. I want to define the state of stress. So will there be infinite stress components as I shift my directions, or are they all related? This is the question which I am posing, and that is what I am going to answer in the next few minutes. That as we change the orientation, we will get different components of traction vector. Are they related to each other or are they not? And if they are related to each other, how are they related to each other? So, yes. No, yeah, but see, now we are talking of a cut inside a body. See, this n is unique if we are at the surface of the body. But now the cut we are making is anywhere inside the body. So we are talking of forces acting on the body from the other parts of the body. So this is internal to the body. You're right. Your question is very valid. On the surface of outer surface, there will be only one n. But if I'm cutting the body, I can cut it at any orientation. So that is what I'm now. See, just as we have velocity at each point, we have traction at each point. But this traction is a function of area. And at least some of you asked me a physical interpretation of a second order tensor. Now you can see that this quantity which I'm going to define, there is a traction vector, force vector, and there is an area vector. And in some sense we are combining these two. And the combination of these two eventually will turn out to be a second order tensor. So that is what we are getting to. But before that, I'll just talk of when we talk of a linear function and I say y is a linear function of x, then how can I represent this? How will I express this mathematically? Y is equal to ax plus b, so this I can write. The mathematical way of writing it is y is equal to ax plus b or alpha x plus beta. And by shifting the origin to beta 0 comma beta, I can make it as y is equal to alpha prime x, or y prime is equal to alpha prime x by shifting the origin. So linear function means y is a function of x. Now, if I generalize it to a vector, if I say A vector is a linear function of vector B. Okay? Now I want to generalize. Now, when I say vector A, then if I have my coordinate axis, it will mean A1, A2, A3. A1i plus A2j plus A3k. And what will be vector B? B1i plus B2j plus B3k. So when I generalize this, what it will mean is the A1 component of the vector will be since it's a linear function, so it can depend only on the components of B in a linear way. So the most general way I will write A1 component will be some coefficient which does not depend on any B times B1 plus another coefficient B2 plus B3, and I use the coefficients as lambda 1, 1. Why do I use two subscripts? Because I have A2 and A3 also. So then if I expand this further, I will get A2 is equal to lambda 2, 1 B1 So this would be the most general way of expressing a vector A, which is a linear function of vector B. Is that fine? That seems to make sense. I'm not going to go too much into maths, but this is probably, so therefore, the point I'm getting to is that how will I write this in a general tensor notation? I will write it as A sub I is equal to in our summation convention, this will become A sub I is equal to lambda ij bj, and lambda ij we can show will be a second order tensor which is not a function of B. So this is how, and so what we do is we take a tensor product of the second order tensor and the vector and we contract the two. So that is what gives us a general linear vector, a vector which is a linear function of another vector. Okay? I am going to use this fact a bit later, so that's why I first did this. Now let us look at this quantity. We talked about traction. Suppose we have a body and we cut it into two parts. Sorry. I wanted to make the left only, I made the full thing. So, pardon me for my drawing. I choose, when I cut the body, I choose two identical areas on the cut section, which means that when I merge the two bodies, these two areas will be identical, or they will merge onto each other. Okay? So now here, if the outward normal is n1, what will be the outward normal on the right side? It will be obviously minus n1. So if this normal is n1, so normal on LHS is n1, normal on RHS will be minus n1. And let's say if T1 is the traction vector on LHS and T2 is the traction vector on the right hand side. Now, this cut we have made is an artificial cut, and we have these two traction vectors. When we combine the two bodies, what can we say about T1 and T2? These internal forces have to be equal and opposite, because when it is a total body, there is no internal force. This internal force which we have, or you can look at it in terms of Newton's third law, that the force which the area on the right hand side exerts on the left has to be equal and opposite to the force which the area on the left hand side exerts on the right. So therefore, what we have is T1 plus T2 must be equal to 0. Is that clear? Because the internal forces have to cancel out. So from here what we get is T1 is the traction force on the vector n at this point P, and T2 is equal to the traction force with the orientation minus n. So therefore, T of n at any point will be equal to minus T of minus n. So this is a property of a surface force which is there. If a surface force has to be there on the internal section of a body, then it has to be an odd function of the normal. Okay? So this is to be there with any surface force. Now, let us try to find the relation between different components of traction force for an arbitrary surface. So we'll use this property, but let's now let us consider a small, let's consider an origin, let's consider a small tetrahedral element. An element which has basically x1, x2, x3, we make 3 points, we join the surfaces. So now this total volume element which I look, how many surfaces it has? It has 3 surfaces which are aligned to the 3 planes x1, x2, x1, x3 and x2, x3, and an inclined orientation which is the thing. Now on each of these. So now this is a if you want to make like simple, you could think of just a triangular element. Okay? This is just a generalization. If you look at a planar case, it will be a triangular element. Okay? So now, so let's say this is O, and let me name these. This is A, this point is B, and this point on the top, this is C. So, let's say this is one. So we have these 4 areas, OBC. Let's look at OBC. I call it as area delta A1. Why do I call it delta A1? Because the normal to the area ABC is in minus of A1 direction, A1 or minus A1, and we'll use the minus sign also. But I call it as delta A1. And similarly, OAC, its direction is minus N2. And OAB, its direction is minus A3. It's the Z direction. Does everybody see that? And the slant area which I have taken, I call it as delta A. Okay. Now, if I look at the surface forces on each of the areas. The surface force on OBC is equal to Fi. Now I represent the normal on that area as minus E1 multiplied by, or sorry, I should use Ti. I have not used F, I have used T for the traction. So this should be so whatever is the traction force on this, it will be Ti. Bracket minus E1 tells us that this is the direction of the normal multiplied by delta A1. Similarly, I can do it for all the forces, all the surfaces. So what I will have will be Ti of minus E2 delta A2, Ti of minus E3 delta A3. This will be the force on OAC, force on OAB, and Ti times N on delta A. This is the force on ABC. Obviously, Ti of minus E1 is not equal to Ti of minus E2. This bracket shows that it's a function of these areas of these directions, and these are all the 4 surface forces. Now, delta A1 is equal to n dotted with E1 gives me the direction cosine of the direction n with the 1 axis, and n dotted with E1 multiplied by delta A, sorry, this on the right side. Why am I? Delta A1 is equal to n dotted with E1 delta A. Similarly, delta A2 So now on this tetrahedral element, I apply Newton's second law or Euler's first axiom, which is sum of external forces is equal to m times a. Okay? Now, which are the external forces which are acting on this tetrahedral element? Sum of all these forces which I have written. Is there any other force which acts on this? In general, the gravity will also act on this. So therefore, what we will have will be sum of external forces will be sum of surface forces plus and body forces. Now, the surface forces, this will be equal to, this sum will be equal to Ti of n delta A plus Ti of E1 Ti of minus E1 Ti of E1 times N1 Ti times delta A is the force acting on the inclined surface. Ti of minus E1 times delta A times N1, where N1 is basically n dotted with E1, is the force acting on 1, and so this is the sum of all the surface forces. Now, the body force will be rho g times delta v, and mass times acceleration will be rho delta v times acceleration, where delta v is the volume of the tetrahedron, and sum of all these must be equal to 0, or sum of all the first 5 terms, 4 terms on the top plus rho g dv must be equal to rho A delta V. Actually, I should have put it as rho GI and rho AI. Instead of, I've mixed the two notations here. If you realize, I've used the tensor notation in the first four, so this should actually be rho. So I can write this as now what we will do is we will shrink this volume to a point, because we are looking at what is happening at each point. So as we shrink the tetrahedron to a point. So if each side is, let us say each side of this tetrahedron is of order delta. That means OA is equal to delta, OB is equal to delta, OC is equal to delta. Then what happens is delta V is of order delta Q and delta A is of order delta square. Okay? Because the volume, when we say, it will be a product of these three linear elements, so it will be of order delta Q, area will be of. So as we shrink to a point, what happens to the delta V terms as compared to the delta A terms? The delta V terms will go to 0. As we shrink our volume to a point, as we shrink the volume to a point, the delta V terms, they go to 0 as compared to delta A. And since we have 4 terms with delta A, see, suppose there were only delta V terms, then we would have had to say sum of all these have to be of the same order. But since we have terms containing delta A as well as delta V, so the delta V terms will go to 0, and what we will get is Ti of n times delta A is equal to Ti of E1 N1 delta A plus Ti of E2 N2 delta A plus Ti of E3 N3 delta A. So all the surface forces will be balancing each other. So we get Ti of n delta A is equal to Ti of E1 plus Ti of E2 plus Ti of E3. And now if delta A goes away, so this gives us that. And here when I have used this, I have also used the fact that Ti of E1 is equal to minus Ti of minus E1. So when I took it on the other side, I changed the sign. Because there was a minus E1, so I have made it E1 now. So this gives me that T sub I of n is equal to Ti of E1 N1 plus Ti of E2 N2 plus Ti of E3 N3. And what this implies is that Ti is a linear function of the normal vector. Since we can write Ti, this traction vector is a linear function of the normal vector. So this means that we can express, and this is where so this implies that Ti is equal to a second order tensor contracted with n. And so I can write Ti is equal to sigma ij nj. The second order tensor which is there, this is what I had stated earlier, that if we have a linear function we can express it as in this form. So I can write Ti is equal to sigma ij nj, and the sigma ij is what we will call as the stress tensor at a point. So the traction vector can be written in form of a stress tensor. So that means while there are infinite directions, but if at a point we specify sigma ij, then we can get the traction vector at any direction using sigma ij. And how many components does sigma ij have? 9 components. So basically we need to specify the 9 components of stress, and that will give us the traction force at any orientation at that point. So sigma ij is what we call as the stress tensor. And if we look at sigma alpha alpha and we say that there is no summation on any Greek index. So sigma alpha alpha means when alpha is 1, we are talking of sigma 1 1. When alpha is 2, we are talking of sigma 2 2. And when alpha is 3, we are talking of sigma 3 3. It is different from sigma ii, because sigma ii would mean sigma 1 1 plus sigma 2 2 plus sigma 3 3. But that's why we say, we always write this no summation on Greek index. So sigma alpha alpha, this will represent the 3 components of the normal stresses. Okay? So that means if at a point I take an area, I cut it perpendicular to the x-axis, sigma xx will give me the force per unit area along the x-axis. Sigma yy means I cut an element perpendicular to the y-axis, and the normal stress along that direction will give me sigma yy. And I cut at the same point an element perpendicular to the z-axis, then the z stress component, force per unit area, will give me sigma zz. And sometimes in solid mechanics, we, instead of using sigma alpha alpha, your textbook, for example, you will see uses only sigma alpha, because the second alpha is not this thing important. So that's why it's called, so this represents the normal stress. And if we look at sigma alpha beta, where alpha is not equal to beta. So this will give me force in alpha direction on an area whose normal is in beta direction. So this will be a component which we will call as the shear stress. Sigma alpha alpha will be the normal stress. Sigma alpha beta will be shear stress. And in solid mechanics text, shear stress is denoted by, instead of using the symbol sigma for the shear stress, the books use a different symbol which they call as tau. That means the stress tensor, if I write sigma xx, sigma xy, sigma xz, this is represented as sigma x, tau xy, so this is just a notation. So as all the solid mechanics texts, they use the sigma and tau notation instead of sigma ij. Okay? So now let me just try to show this on a, let's look at a planar case. So I make a small rectangular element along around the origin. I have my x and y axis. So the surface forces on this, let me use a different color. Let me denote the surface force per unit area by red color, and this, so basically on this element sigma x will be the stress which is acting, and if I have to find the force acting in the x direction on this right face, what will that be? Sigma x multiplied by, now let's say this is delta x, this is delta y, and in z direction the dimension is unity. So if the stress on this face is sigma x, what will be the area in the x direction on this? It will be sigma x multiplied by delta y times 1. So the x force on the right face will be sigma x times delta y times 1. Okay? And similarly on this, the stress component, the shear stress component on the right face will be given by tau yx. The force is in the y direction, that's the first index. X is the direction of the area. So this is tau yx, and when we multiply it by, to find the y force on this face, it will be tau yx multiplied by delta y. So these are the stress components. And x force on the right face, this will be equal to sigma x times delta y times 1. Okay? Now, similar to this, there will be forces acting on all the four faces. Okay? So what will be the force, or how will we represent on the top face? We will represent this by sigma y, or which is the same as sigma yy. And what will be the notation of this horizontal stress which I have shown? It will be tau what? Tau xy or yx? xy. The force is in the x direction and it is on the y face. So therefore this component of stress will be tau xy. And the force will be sigma y multiplied by delta x. And the x force will be tau xy multiplied by delta x. Okay? Now, if this element is if it is at a small point and if this is to be, what we do is, on the left hand side, the normal is in the minus x direction. So, sigma x here is shown in the minus x direction, because these two have to balance out. So, sigma x on the negative, what we show is any area or a face, what we call, depending on the direction of the normal, we call it positive or negative. If the direction of the normal is in the negative direction, we call it a negative face. And there, if the force is positive, then it will be shown in the negative direction. What does a positive sigma x do? It tends to pull. What happens if magnitude of sigma x is negative? It will tend to compress. And it has to do that on both the faces. So therefore, the way sigma x is represented on opposite faces, its direction will be opposite. On the negative face, a negative direction of force is a positive sigma x. Okay? So similar to this, we will have a tau yx, and then we have a sigma y and tau xy. Okay? Now, this picture tells us one more thing. Suppose I have only tau xy acting and tau yx is not there. If I have this element like this and tau xy is acting, tau yx is 0, let us say. What will happen to this element? It will keep on rotating. So now if the element has to be in rotational equilibrium, what can we say? Tau xy must be equal to tau yx. That means if I have a shear stress on this direction, then for the rotational equilibrium, a complementary tau xy also has to act, otherwise this element will keep on rotating. So if the element has to be in equilibrium, what can I say about tau xy and tau yx? Tau xy has to be equal to tau yx. Okay? So this is, I'm just giving you a physical feel of this, and we can generalize this also. But let's first talk of this. What we have shown is, and I'll return to this part a bit later, what we have shown is that Tij, we wrote it as sigma ij nj, where sigma ij is a second order tensor. Now based on this, I get to this relation which is called the transformation relation, that if I know sigma Lm, if I know sigma ij for x, y, z, and if I rotate my axis to a new position x prime, y prime and z prime, then the components along the rotated axis will be given by this relation. Sigma ij prime is equal to ALI, AMJ, sigma LM. Now AIJ or ALI, these are the direction cosines. That means cosine of the angle between x sub L and x I bar or xi prime. The new x's are prime, the old x's is without prime. Cosine of the angle between xl and xi prime is given as ANI. That means A11 is the cosine of the angle between x1 and x1 prime. A12 is the angle between, cosine of the angle between A2 and A1 prime. So if it is A21, A22 will be the angle between x2 and x2 prime. And this, at least for a 2 by 2 case, you know, it becomes, the matrix becomes equal to cos theta sin theta minus sin theta cos theta. So it will take a form like this. So you have to just work out, and we will see how to work this out. Just keep this relation in mind. This is the transformation relation for sigma ij. I will return to this. Now, let me derive and since so far this definition and the way I have defined this stress, other than calling it sigma and tau, this whole thing is valid for solids as well as fluids. A stress component, what we have talked about, is the same in a fluid element as well as in a solid element. So I have not made any differentiation between a solid and a fluid, other than a small thing about the nomenclature which solid mechanics texts somehow use only tau for the shear stress and sigma for the normal stress. But other than that, if we look at the notation, okay, another thing you may find if you follow some really classical books, you may find what I have used sigma ij. I have used I for the direction of the force, j for the direction of area. In some books, they do it in a reverse way. So that, don't be confused with that. We will follow one consistent notation. We will use the first index for force, second for the area. But it could be done with the other one and it won't make a difference. Okay. So, yeah. Oh, that's the length. This element is delta y and delta x. So these are just the dimensions. Maybe I should have used another color. So this is not a force. Okay. Okay. So now all I am going to do is write Newton's second law for a material element for a small point. So let's see how we do that. So suppose we have a material, I am just showing it like this, which may be a solid or a fluid, and I choose a small volume delta V. Now, Newton's second law tells me sum of the forces on this is equal to m times a. Now, So this I can write, just let me write this. The left hand side is rho dV times A sub I. A sub I is the acceleration multiplied by mass rho dV, and if I integrate it over the volume, it will give me the total mass times acceleration on this volume dV. So I integrate over this, this is ma. So this is the basically ma term, and this must be equal to the body forces plus the surface forces acting on the element. Now the body forces are what? Is gravity. So rho dV times g sub I, and I take a volume integral of this. So the total body force is equal to m times g, so rho dV times g sub I. Now basically taking these integrals and all lets me have different values of g at different points. And similarly on the left hand side, different points can have different acceleration. Okay. Now the surface forces will be equal to, now on this volume, sigma ij nj will be the total surface force. Okay. And if I have to integrate it over the surface of the entire this thing, so that will give me the total surface forces. Sigma ij nj, when I sum it over all the normals, that is what is the total surface force. So this is what I have, that volume integral is this. Now what I do is, use Gauss's divergence theorem, and this becomes equal to volume integral of the divergence of sigma ij. Because the index there is nj, so therefore I have to take a d by dxj. I am taking a dot product with n. So by Gauss's divergence theorem, this becomes equal to d by dxj of sigma ij dv. So what I get is the volume integral of rho ai minus rho gi minus partial by partial xj of sigma ij dv is equal to 0. I combine everything on the left hand side, I get this equation. एक बार आज ऐसा करो प्रकाश, काउंट कर लो कितने बच्चे हैं और कितनों की अटेंडेंस है. अटेंडेंस हो गई ना पूरी? एक बार काउंट कर लो, सो दैट विल नो प्रॉक्सी है कि नहीं है. और होगी तो फिर मैं चेक कर लूँगा. अभी अगर किसी ने प्रॉक्सी लगाई है तो अभी टाइम है, आप काट दीजिए. हाथ उठाइए और जिसकी आपने प्रॉक्सी लगाई है काट दो. मैं कुछ नहीं कहूँगा, मैं देखूँगा भी नहीं कौन काट रहा है. किसी ने किसी की प्रॉक्सी लगाई हो तो प्लीज़ काट दो अभी लेके. आई एम गिविंग यू अ चांस. किसी को कुछ नहीं कहा जाएगा, मैं तुम्हारे शक्ल भी नहीं देखूँगा. पर अगर वो पकड़ी गई प्रॉक्सी, तो जिसकी प्रॉक्सी लगी है उसके तो बैंड बज गए. लगाई है आपने किसी की तो हटा दो. अगर किसी ने भी, आई एम नॉट लुकिंग एट यू पॉइंटेडली, दिस इज अ जनरल. अगर किसी देयर इज अ चांस, अभी अपने हाथ उठा के आप प्रॉक्सी काट दीजिए अपने दोस्त की. किसी को हाथ उठाना है दे दो, या ओके प्लीज लेटर आप काट दीजिए, कोई बात नहीं, आई एम नॉट लुकिंग एट, आई डोंट इवन केयर, इट डजंट मैटर, बट लेट्स नॉट, एक बार तो दोबारा पास कर दो भैया, प्रॉक्सी वाले काट दो सारी, और प्लीज इतनी दोस्ती मत दिखाओ, दोस्ती हमने भी बहुत की है, दोस्ती मतलब पर हाँ, और भी पास कर दो, जिसको काटना है काट लेगा, ओके, लेट्स नॉट रेज हैंड्स, पास ऐसे ही कर दो, आई शुड हैव डन दैट, ओके ओके. Now you see, I have got this relation, a volume integral is 0. Now this is valid for every point. This relation is valid for every delta V. What does that mean? That that whatever is the integrand, that has to be 0, because it is valid for any arbitrary V. See, for example, if I have a definite integral a to b, something is 0. That will not mean that the integrand is 0. But if it is valid for any arbitrary a and b, that will mean the integrand also has to be 0. So therefore, we use this argument, since this expression is valid for any arbitrary v, this implies that the integrand has to be 0. And so we get this relation rho times ai is equal to rho times gi and this is what we call as Cauchy's equation. This is valid for any material, solids, fluids, and that's why probably doing it in this way in this course makes a bit of more sense, that this is a general equation. As long as Newton's law is valid, this is valid. Now for Newton's law to be valid, the only condition we have is that the acceleration has to be measured with respect to an inertial frame of reference. That is the only condition which we have, that the acceleration has to be with respect to an inertial frame, then this is valid. Okay? So this is Euler's first axiom. Euler's second axiom was what? Torque is equal to I alpha. We talked about the moment. So this is now and if I apply Euler's second axiom on an infinitesimal element, now let's see, we'll take a 2D case. This is O. At O, the stress components at the origin, we take them as sigma xx, sigma xy. So I'm just reverting back to sigma. It could be tau, I can use tau also. Sigma yx, sigma yy. These are the stress components at point O. So now, again let's say this one, this is delta x and this is delta y. So rectangular element The stress component on the face AB will be sigma xx if I expand in a Taylor series on the face AB at O, the stress is sigma xx. So on AB, it will be sigma xx plus partial sigma xx by partial x times delta x by 2. Okay? This is just a Taylor series expansion, and sigma yx will be sigma yx plus sigma yx by partial x into delta x by 2. Now, what will be the forces because of this? Yeah. So this is just I'm expand. See, I have sigma xx, sigma xy, all these functions of x and y, and they are given at point O. So now I'm shifting them. I want to find what is sigma xx at on this AB. I'm moving by, I'm looking at the variation of sigma xx. So therefore, on face AB, what will be the value of sigma xx? It will be sigma xx plus, if sigma xx is known as a function of x and y, partial sigma xx by partial x multiplied by delta x by 2. And similarly, what will be it on face CD? Minus of that. The first quantity will be the same. It will be this, and it will point in the minus x direction. Similarly, I have sigma yx, and same thing for the other, all the four faces. Okay? So now these are the stresses. So I'll just write what are the force, surface force on AB. In the x direction, it will be sigma xx So the x and y component of forces on AB will be the stress component multiplied by the area. So now we will have this on all the four faces. Okay? So we will have basically total of 8 surface forces acting in the x and y directions. 2 forces on each face. Okay? Now if I apply torque is equal to I alpha about the center, about the origin, then I have to take the moments because of each of these forces. So on the force AB, let's look at just one face. We'll have to do it for all the 4 faces. What will be the moment due to the x component? That will be 0. Because if force is passing in the x direction and I am taking the moment. So the moment will only come because of the y component. Okay? When I look at the the horizontal face, the moment will only come because of the sigma xy. Similarly on the other 2 faces. Okay. Now this moment when I calculate, it will be this force multiplied by delta x by 2 or delta y by 2. Delta x terms will be multiplied by delta y with delta x. Okay? So that means these terms are multiplied by 2 deltas, delta x and delta y. Now when I look at the body force, rho g passes through the center, there is no moment. And if I say moment due to acceleration, whatever is there, that will also cancel away. Or even if that you take moment about some other point, then their order will be one order lower, because that will be delta V. So it will be delta x times delta y. And then you have to take a moment. So therefore, what will happen is, when you do all this, what you will get, what do you expect, what will come out? And this is what I was referring to when I drew the figure earlier. I will write it out and put it in the notes when I do it, but what this is going to lead to is sigma xy will be equal to sigma yx. The two complementary stresses, shear stresses which are there, they will have to be equal. Otherwise, we will not have torque is equal to I alpha. And this is what I was saying. So therefore, when a moment balance will imply sigma yx is equal to sigma xy, or this will lead to, and this is what we call and this is valid for any material, that because in doing this we have not made any assumptions. So whether the material is solid or fluid, or it changes properties in a direction or not, the shear stresses are always, the complementary shear stresses have to be equal. So that means if a tau xy is coming, a tau yx also has to come on a perpendicular face, which has to be equal to tau xy, so that the equations of motion can be satisfied. So this is a very general relation, it holds under all conditions. There is only one condition when it may not hold. Just as we have body forces, if there is a couple which is acting at per unit volume, then when we calculate, then that term will not cancel out. And body couples normally are not there, only if there is some electromagnetic force acting which causes a couple, which is acting at each point. Then the difference of these stresses will be causing that couple. But otherwise, this is a fairly general relation. Shear stresses are complementary. Okay. Now, I believe till now what we have done, all of this has been a lot of derivations. Now, my focus will not be so much on derivations. I may ask some small things on tensor notation as I have given you in the homework. But as far as the derivations of these equations go, we will not be really we have derived the equations for a completeness sake, and also so that you know what assumptions are being used at what stage. But overall, in the course now, I am going to start on the physical aspects from now onwards. But one thing which I am going to do is I will make a small deviation. The first part of the course, I will do a bit of things which have been done in chapter 7. That is, we will look at how stress components transform. We will start with that, and then we will come to chapter 1, chapter 2, and so on. So in the next class, I am going to look at the transformation of stresses. Given stress components along some components, how do we, if we rotate the axis, so we will see how to expand this relation which I said, sigma ij prime is equal to aki alj sigma KL or whatever it was. So we will look at how to see that relation mainly for a two-dimensional case. Simple relation. So that is what I will start with, and then we will continue. Okay.